Hi, my name is John Ford and I teach drilling engineering here in the Institute of Petroleum Engineering. And today what I'm going to do is run through the tutorial on well control. First of all, let's have a look at the question. The question presented here is in the same format as it will be presented in the exam. So it says, whilst drilling the 12¼ inch hole section of a vertical well with a mud weight of 10.5 pound per gallon, the driller detects a kick. The well is shut in and the following information is gathered. So there we have all the numerical information we need to solve the problem. And at the bottom you see I ask you to calculate and discuss the following. I'll come back to that issue of discuss in a moment. The type of fluid that has entered the wellbore and the mud weight required to kill the well. So let's start. The first thing we have to do is to draw a diagram of the situation which has been described in the question. You should always draw a diagram because it will help remind you of what you're actually dealing with, and then also means that you don't have to keep referring back to the question. So let's have a look what we've got. Well, the first thing it says is that the situation in the wellbore is as follows. We have 13 3/8 inch casing set down at a depth of 3,800 feet. Then we've been drilling ahead and we drill all the way down to a depth of 7,250 feet. And this is, of course, a 12¼ inch hole. Okay, so now we'll draw in the drill string. With the drill collars at the bottom. There's the drill pipe. There's the drill collars, and then the drill bit at the bottom. Okay, and we are told that it was a 12¼ inch hole, 7,250 feet, previous casing shoe, depth of the casing shoe, leak-off test pressure at the previous shoe equals the equivalent of 0.85 psi per foot. Okay, and BHA is 400 feet of 9 inch by 2 13/16 drill collars and 5 inch drill pipe. And of course, once we take the influx, I'm not going to draw that in just yet, but when we do take the influx, we will close the well in at surface, up here on the BOPs, and we will have a PDP and a P annulus, pressure on the drill pipe, pressure on the annulus. And the PDP, we're told, equals 700 psi, and the P annulus equals 900 psi. And there has been an influx at the bottom of 33 barrels. Just put that on. Okay, so what we've done there is we've captured all of the description or the description of the situation when the kick occurs. All the information, numerical information from the question. So I can just refer to this now rather than having to go back and forward to the question, which is on the previous page here. But rather than have to go back and look at all of these over and over again, all that information has now been collected into one diagram here. Okay. So now the easiest thing to calculate here, to be quite honest, is the mud weight required to kill the well. So although that's the second part of the question, I'm going to do that first. So I'm actually doing number 2 first, and this is kill mud weight. Okay. Okay, so what do we got? Well, if we look at the drill pipe pressures, just underline that. Well, if we look at the drill pipe here at surface, what we see is drill pipe, and we draw a right little equation which describes the situation. What we get is that the pressure in the formation from which the kick was taken, that is down here, PF, must, when everything is static, when everything is closed in, equal the density of the mud inside the drill pipe times the depth of the hole plus the pressure on the drill pipe at surface. It must equal this, because if this side of the equation, that is the hydrostatic head of the mud plus the pressure at surface, were greater than the pressure in the formation, then we would have flow in this direction. If the pressure in the formation were greater than the hydrostatic plus the pressure at surface, we would have flow in this direction. But since everything is static, we know that this equation must be true. So now what do we know in this equation? Well, let's just tick them off. I often find that's useful. What do I know? Well, I do know the density of the mud that I had in the well when I took the kick. I know the depth of the well, and I know the pressure at surface, and therefore I can get PF, i.e. the pressure in the formation from which I took the kick. So let's do that. PF therefore equals rho m times, let's calculate this out, this is 10.5 times 0.052 times the depth, which is 7250, plus pressure at surface on the drill pipe, which is 700 psi. So all of that equals 4,658.5 psi. That is the pressure in the formation. Now, how do I determine the kill mud weight? Rho kill mud equals PF, pressure in the formation, divided by D. In this case, 4658.5 divided by 7250 equals 0.64 psi per foot, or in pounds per gallon, 12.4 ppg. And that's what I was looking for. So, some of you notice that I haven't included in here any overbalance. Well, what I do then is I make a note, and this is where that calculate and discuss in the question comes from. This is the discussion. There are two points to note here, 2 points that you must state in your discussion. The first one is that an overbalance of 200 psi would be added, or will be added, would be added before drilling ahead. In other words, I'm going to kill the well with the 12.4 pound per gallon mud, but then before I drill ahead, I'll add an additional 200 psi to this pressure here, which will give me an overbalance of 200 psi over the formation pressure, and that is the mud I'll use to drill ahead. Now, the reason we do that is because there is a risk that when we circulate this mud into the hole, that we'll actually get fracture if the mud weight is too high. So what we do is we limit the level of the mud weight to the minimum required simply to balance the pressure in the formation. Then when the well is killed, then we can add the additional overbalance of 200 psi, an additional mud weight. The second point to note is that if you compare this pressure gradient here, 0.64 psi per foot, with 0.85, it's quite clear, and we should always check this, that the kill mud weight is much less than the leak-off test pressure strictly speaking gradient, leak-off test pressure gradient at the previous shoe and therefore losses are not expected when killing the well. Now, I would want those two notes to be presented in the solution for such a question. Okay? Because they're absolutely critical from a well-controlled point of view. Okay, so let's go on to the first part now. Now I'm going to use the bottom of this page. I'm going to try and get everything onto one page so we can keep an eye on everything. So the second part of the question was to determine the type of influx. Whoops. Now to do this we must look at the annulus pressures. And once again, if everything is in equilibrium, we can say that the PF, pressure in the formation down here, must equal the hydrostatic pressure in the annulus space here. Now that will be made up of two parts. The part at the bottom, the hydrostatic pressure due to the influx, and I'm not drawing this in yet, and you'll see why in a second, and then the hydrostatic due to the mud above that. So what do we have at the very bottom? And I always find it's best to work from the bottom up here when writing this equation. Right at the bottom we'd have the hydrostatic due to the influx plus the hydrostatic due to the column of mud that was in the well whilst drilling, and now we're going to call that H annulus because it's not as up here depth, because of course we've got some influx at the bottom, so it's H annulus, which is the height of mud in the annulus, plus the pressure at surface on the annulus. That equation has got to be correct if everything is in equilibrium. Now, before I can calculate this, well, first of all, let me just go through and see what I know and what I don't know. So, first of all, do I know the density of the influx? Well, no, that's what I'm trying to determine. Do I know the height of the influx? Well, I don't know it directly, but I do know that I got 33 barrels of fluid here. So I know the volume of influx, but I don't know the height of the influx. Do I know the density of the mud in the well when drilling ahead? Yes, I do. Do I know the height of the mud in the annulus space? Well, no, I need HI in order to get that. But HI and HI are linked, of course, because the sum of the two has to equal the total depth of the hole, which we do know from up here, 7250. Do I know the pressure on the annulus at surface? Yes, well, of course I do. Okay, so what I need to do over here then is I now need to work out what the height of the influx is at the bottom of the hole. I'll just do it over here. Now, a very good idea here, I'm going to do this in another color just to identify its separate calculation, is a very good idea here, approach to this, is first of all to calculate the annular volume opposite the drill collars. And that equals 400 times, now in order to get to do the other part of this question, you need to look at the second page of the question where I give you the annular capacities or volumetric capacities in the annular spaces. And on that sheet you will find that the annular capacity opposite the drill collars, basically between the drill collar, that's the 9-inch drill collar, and the 12¼ inch hole, will be 0.0671 barrels per foot. Now if you multiply that out, what you get basically is an annular capacity there of 26.84 barrels of whatever is in that annular space. Now that's very interesting because you notice we've got a 33 barrel influx. So that means, I'm just going to draw it here, that means this entire space is full of influx, because it says here that is 26.84 barrels, but it means that some of that influx is also up here, opposite the drill pipe. In other words, the height of the influx is a combination of the height opposite the drill pipe plus the height opposite the drill collar. Well, we know the height of the drill collar, that's 400 feet. So all we need to do now is to determine the height opposite the drill pipe. The way we do that is basically to say, okay, the height opposite the drill pipe will equal the 33 barrel total influx minus 26.84, which is opposite the drill collar. So that tells us there's something like, oh, that'll come out to be about 6.16 barrels opposite drill pipe, divided by the annular capacity between the drill pipe and the borehole, which again is given in the attachment volumetric capacities as being 0.1215 barrels per foot. If you divide that out, what you get basically is 50.7 feet. So this means that the total height of the influx equals HDC plus equals HDP, which equals 450.7 feet. 400 plus the 50.7. So now I know what HI is. I can obviously get HN because HN equals the total depth minus 450.7. So I can also get HN, which means in this equation, PF of course I can get from up here. I've already calculated that as being 4658.5, so I know that. So the only thing remaining in this equation that I don't know is rho I. So let's put all these terms in. So PF equals 4658.5 equals rho I times 450.7 HI plus rho M, which is basically 10.5, which is our original mud weight, times 0.052 times, it's basically 7250 minus HI, which in fact is 6799.3, plus P annulus, which we know from up here, is 900. And if you calculate all that out, you get rho I equals 0.102 psi per foot, which is therefore clearly influx is gas. Okay, so that's basically the entire calculation, and if you present it like that in the exam, that would get you full marks. Okay, well thank you very much, and I'll be preparing another video like this on the various other questions which I've posted in the assignments.